Hi, this is Tzvi Rosen with our last lecture in the matrix theory course, and this time we'll peek forward to chapter 6 in the textbook to the topic of inner products. And this generalizes the dot product which we saw in the last lecture. So we'll start by defining an inner product, and the way we define this is using a set of axioms. The inner product is a function taking u and v in a vector space V, and it returns a real number, which is signified by angular brackets u comma v, and it satisfies the following properties. First, uv must be equal to vu. Okay, this is called symmetry. We don't want the order that you do the inner product in to matter. Second, we have u plus v inner product with w is equal to u product with w plus v product with w. And this is called additivity in the first argument. And like a lot of linear algebra and matrix theory, additivity is a nice property to have. Property 3, if you have u scaled by a real number k and take the inner product with v, it's the same as taking the inner product with v, taking the resulting real number and multiplying it by k. This is called homogeneity. Okay, and that connects to other areas of math that are not worth going into right now. Finally, we have that the inner product of v with itself must be non-negative. And if it's 0, that is only possible if v itself is 0. So if v is a non-zero vector, the inner product with itself must be strictly positive. Okay, so those are the 4 properties, and a real vector space with an inner product satisfying these properties is called a real inner product space. One more aspect of this definition, particularly related to the final property here, is that the norm of a vector, signified by 2 vertical lines on each side of the vector, is equal to the square root of the inner product of the vector with itself. Okay, and this is well defined because we know that the inner product of a vector with itself is always positive, or always non-negative at least. Okay, so let's see some examples. First example, easiest example, is a dot product, okay, which is what we saw in the last lecture. And let's assume we're in Rn, and let's just verify each of these properties. So for the first property, if we assume that u is equal to the vector u1 through un, and v is equal to the vector v1 through vn, then the inner product uv is equal to u1 v1 plus up to un vn. Okay, and each of these is just normal multiplication on the coordinates. But that's obviously equal to v1 u1 plus up to vn un. And that's the inner product of v with u. So clearly we have symmetry in the dot product. So let's look at property 2. Okay, so here we're going to add in w, which will be w1 through wn, and we have u plus v inner product with w is going to be u1 plus v1 times w1 plus up to un plus vn times wn. And you can distribute that multiplication to get u1 w1 plus v1 w1 plus up to un wn plus vn wn. And this is just by grouping the terms differently, you'll find that this is equal to uw plus vw. Okay, so we also have additivity. Okay, now let's try to get homogeneity. So if we have ku inner product with v, well, the vector ku has coordinates ku1, and that gets inner product with v1. So we're multiplying with v. So we're multiplying the coordinates, the first coordinates of each vector. And then we plus this up to k un vn. But by associativity of multiplication, this is the same thing as k times u1 v1 plus up to k times un vn. So I can just factor out the k, and what's left is the inner product of u and v, the dot product of u and v, so it has homogeneity as well. Finally, we want to check that the inner product of v with itself is non-negative. Okay, well, that's not so hard, because if we have the dot product, we're taking v1 times v1 is v1 squared plus up to vn squared. Okay. Each of these is a square of a real number, so it's positive, or so it's non-negative. So each summand is non-negative, so the sum is also non-negative. Sum is greater than or equal to 0. How do we know that v inner product with itself is 0 only if and only if v equals 0? Well, certainly, okay, so if v equals 0, then the dot product is obviously 0. But how do we get the other way? So knowing that the inner product is 0, well, that means that we know the formula. It's v1 squared plus up to vn squared. But that means that if any single one of these would be strictly positive, that would mean that the whole sum would also be strictly positive. So the fact that this equals 0 means that every vi squared is 0, which means that v itself is the 0 vector. Okay, so we have the fourth property as well. Okay, so the dot product is our first example of an inner product. Now let's consider a weighted dot product, and this is a little bit different. It looks a lot like a dot product, but what's added is these new positive numbers called weights, w1 through wn. For vectors u and v and rn, we define the inner product to be w1, so the first weight times the product of the first coordinates, plus second weight times product of the second coordinates, etc., up to nth weight times the product of the nth coordinates. So let's look at, for example, let n equal 2, and we'll let w1 equal 3, and w2 will be equal to 4. Okay? Then that means that the inner product will be uv is equal to 3 u1 v1 plus 4 u2 v2. Okay? For a specific example, if we take, let's take the vector 1 minus 1 and the vector let's make it 2, 1. Then the inner product is 3 times 1 times 2 plus 4 times minus 1 times 1, which gives us 6 minus 4, or 2. Okay? So now we can check the properties for the inner product. So 1 and 2 are not hard to check. I'll let you do that on your own. For that matter, 3 as well. 3, similar to dot product. You just expand out the formula and you show that it works. Okay. How about number 4? So we want to show that this inner product is always greater than or equal to 0. Well, this is equal to w1 times v1 squared plus up to wn vn squared. So it's not clear at first that these have to be that this has to be a sum of positive numbers, but then you remember these W1 through Wn must be positive. Okay? So for that reason, every summand is strictly non-negative. Okay, so we'll point out the Wi's are all strictly positive. And that means that every summand is non-negative, which means in turn that the sum is non-negative. Okay? How do we know that inner product of v is 0 if and only if the vector itself is 0? Similar to the previous argument, if we know that if v1 if vi is not equal to 0 for some I, then the inner product of v with itself gives you wi times vi squared plus some other positive stuff. And if this is not equal to 0, this is going to be strictly greater than 0. So it must be that if the inner product is 0, every coordinate is 0. Okay? Let me write that down. So if VV equals 0, every VI must be 0. Okay. Now let's consider the unit circle. So when I say the unit circle, I'm talking about the vectors v such that, let's make it v in v, such that the norm of v is equal to 1. Okay, and recall that the norm is the square root of the inner product of v with itself. Okay, so if we're using the usual dot product in R2, let's think about what the unit circle is. So we have we have a vector xy, and we're taking the inner product of it with itself. Let's do it in column notation, why not? Okay, and we're going to see that this is equal to 1. So that means that x squared plus y squared is equal to 1. And so the unit circle is what we're familiar with as the unit circle. The lovely unit circle. Okay, how about the weighted dot product in R2? So let's say, again, let's use W1 equals 3 and W2 equals, maybe that might be a little too much math. Let's make it 1 and 2. Okay, so now the inner product xy equals 1 translates into W1, so that's 1 times x squared, plus 2 times y squared equals 1. We can reformulate this as x over 1 squared plus y divided by 1 over the square root of 2 squared equals 1. And you'll recognize this as an equation for an ellipse so this is an ellipse with major axis 1 and minor axis equal to 1 over the square root of 2. And the way that would look is roughly like this. So we have 1 over here minus 1 over here. And then 1 over the square root of 2 is roughly 1 over 1.4, so that maybe let's make that generously 2/3 or so. So if this were 1 and 1, so it would look something like this. So under this inner product, this is our unit circle, this flat ellipse. Okay, so some of our geometric intuitions, though with my with my artistic skills, the circle looks a little bit like the ellipse, but some of our geometric intuition is going to fail us here, because the inner product here defines a different concept of norm and length. Okay, now let's consider an inner product that is very different from the ones we've seen so far, though it's actually a generalization. And this is the matrix inner product. So you can fix an n by n invertible matrix A. And for vectors u and v in Rn, you define the inner product as inner product of uv is equal to A times the vector u, dot product with A times the vector v. We'll take n equals 2, and we'll fix A to be the matrix. So make it not too complicated. Let's make it look like this. Okay. And since it's lower triangular, we can be sure it's invertible. So how would we take the inner product of, let's say, 2, 1, 1 minus 1? Okay. So this would be equal to A times 2, 1, dot product with A times 1 minus 1, which would give us, so it's 2 in the first coordinate, and minus 2 minus 1 is minus 3, dot product with 1 in the first coordinate here, and minus 1 plus 1 gives us 0 here. So we end up with 2 as our result. So that would be the inner product using this matrix product. Okay, well, does this satisfy the axioms of inner products? Okay, well, this can be a little tricky. So the way we're going to do it is first to observe that so uv, defined as au dot product av, could also be written as au transpose, and then using matrix multiplication, av. Okay, so this is when we do the transpose, we have a 1 by n matrix, and this is an n by 1 matrix, so it gives a result of a 1 by 1 matrix whose entry would be the inner product. Okay, so this is going to be uv. But we can manipulate this expression a bit more. So this, when you take a transpose of a matrix product, like A times U, that's the same as transposing and reversing the order. So this is really U transpose A transpose, and then we have, okay, this is in parentheses, and then we have AV. This is really equal to U transpose A transpose A V. Okay, and this is a symmetric matrix. Okay, and so one thing I can do to this whole product is to take the transpose. Okay, so we know this is going to be a 1 by 1. The full product will be a 1 by 1 matrix. So that means that if I transpose the whole thing, I should get the same thing back. Okay, so this transposed should give me V transpose. Again, I'm just reversing the order of multiplication, and and putting a transpose on everything. So this gives me A transpose A, since it's symmetric, and this is U, and this is the same thing as V inner product with U. So this implies the symmetric property. Okay, so that's first. Okay, property 2 is a bit easier. So if we have AU plus A applied to U plus V, dot product with AW, this is given by AU plus AV, dot product AW. We know the dot product is linear. We proved that earlier. So this is the same thing as AU dot AW plus AV dot AW. But that's equal to UW VW. Okay. Pretty nice. Okay. Number 3, so we need to know that KUV is equal to K times UV. Well, this is given by A times KU dot product AV, and this is, because this is matrix multiplication, you can pull scalars out. So this is the same as K times AU dot AV, and this is equal to K times inner product UV. Okay, because you can pull K out of a dot product. Okay, so that gives us the third property. How about the fourth property? Well, if we have VV greater than or equal to, so let's consider VV. This is equal to AV dot product with AV. Okay, well, this is a dot product of a vector with itself, so this is going to be non-negative by properties of the dot product. Okay, well, how do I know if the fact that VV, inner product of V with itself, equals 0 implies V equals 0? Well, first of all, so let's assume that V equals 0. Then the inner product here is equal to AV dot AV, but any matrix times the 0 vector is 0. So this is just 0 dot 0, which is 0. Okay, that's fine. So how about if we know that the inner product is 0? Well, that means that AV dot product AV equals 0. But that means that by the properties of the dot product, so by properties of dot, this means that AV must be equal to 0. Okay? And we specified that A has to be an invertible matrix. Okay, and an invertible matrix has a trivial kernel, so V must be 0. Okay, so that tells me that the inner product is 0 if and only if the vector itself is 0. Okay? Now here we're getting more and more unfamiliar with these inner products. Here's a new one. So if we fix distinct real numbers, x0 through xn, then for polynomials p and q in Pn, which again is the space of degree at most n polynomials, we define the inner product as the evaluation of p at x0 times the evaluation of q at x0 plus up to evaluation at xn of p times evaluation at xn of q. So let's give an example. So let's say let's fix n equal to 2, and we'll have p be equal to x squared minus 1, and let's let q be equal to x. Okay, and we're going to pick 3 points. x0 will be minus 1, x1 will be 0, and x2, let's make it a little bigger, let's make it 4. Okay, then the inner product of p and q is going to be equal to p of x naught, q of x naught, plus p of x1, q of x1, plus p of x2, q of x2. Okay, so let's evaluate these. So let's evaluate the p ones first. So p at minus 1 gives me 1 minus 1, or 0. P of x1 is 0 minus 1, or negative 1. And p of x2 is 15, 16 minus 1, or 15. Okay. How about q of x naught? So let's use a different color. Q of x naught gives us x at minus 1 is just minus 1, and at 0 is just 0, and at 4 is just 4. Okay, now we multiply it out and add them all together. And we get, well, the zeros make this simple, we get 60. Okay? So it's kind of weird. This seems like kind of a weird inner product. Definitely not the same kind of coordinate-wise approach that we've been taking so far. Here we're evaluating a polynomial at different points. But indeed, we can show this is an inner product. So the first property is pretty straightforward. You just kind of write it out. So PQ equals P of x naught, Q of x naught, etc. P of xn, Q of xn, and then you just switch the order, so it's Q of x naught. Multiplication can go in any order. Okay, and that's just the inner product of Q with P. Okay, how about the second property? Let's say we have P plus Q, and then there's another polynomial R. So it's the same idea. So P of x naught. Well, what's the value of P plus Q at x naught? Let's make a note of this. Note, P plus Q evaluated at x is the same as P of x plus Q of x. Okay, just by virtue of how we're defining addition of polynomials, right? If you're evaluating at a certain point, you can evaluate the two functions separately and then just add the result together. So that would mean that P of x naught plus Q of x naught times R of x naught, etc., can be factored as P of x naught R of x naught, or actually can be expanded as P of x naught R of x naught plus Q of x naught R of x naught, etc., which is the same as PRQR. PR plus QR. Okay, two more properties to go. Okay, for number 3, we want to show that KP inner product with Q should be equal to K times the inner product of P with Q. And again, you could just spell it out. So you'll use that KP, that polynomial evaluated at x naught, is the same thing as K times the evaluation of P at x naught. Okay, and then just spell it all out, and you should arrive at the right conclusion. Okay, now PQ must be greater than or equal, sorry, this means PP should be greater than or equal to 0. Well, PP is equal to P of x naught squared plus P of x1 squared, etc., up to P of xn squared. And so this is obviously non-negative because the sum of squares is non-negative. How do I know that PP equals 0? That the inner product equals 0 implies that P itself is 0. Well, PP equals 0. That means that all of these P of x's, P of x naught must be equal to P of x1 up to P of xn must be equal to 0. but the only polynomial that has n plus 1 zeros and degree bounded above by n is the zero polynomial. But because polynomial degree is less than or equal to n, p must be if p has greater than n zeros, then we know that p equals the zero polynomial. Okay, so we've discovered that this evaluation inner product is actually an inner product satisfying all of the requirements. Okay, now here's a weird one, which will look somewhat unfamiliar if you haven't seen calculus in a while. So if you fix an interval in the real numbers, that means kind of a stretch of numbers from some smaller number to some bigger number, like 2 to 5 or -3 to 1,000. So fix that interval, and then let f and g be two functions that are continuous on that interval. We can define the inner product f and g to be the integral from a to b of f of x to g of x dx. Okay, so you multiply the functions and then you integrate over the interval. Okay, so here's an example. We can use the same functions as last time, actually. So we can have f being x squared minus 1 and g being x. And now we can take our interval to be, let's make it -1 to 2. Okay. Then the inner product of f and g is equal to the integral from -1 to 2 of x squared minus 1 times x dx, which is equal to the integral from -1 to 2 of x cubed minus x dx. And taking the antiderivatives using the power rule, we would get x to the 4th over 4 minus x squared over 2, evaluated from -1 to 2, which gives us 16 over 4 is 4, minus 4 over 2 is 2, minus 1 over 4 minus 1 over 2. So we have 2 minus -1/4, or 2 plus 1/4 gives us 9/4. And that would be our inner product. Okay, and I'm going to spare you the proof that it's actually an inner product. Okay, well, with all of these weird new inner products, we can use some of the ideas from our last lecture about vector geometry. So one thing we saw in the context of dot products we knew that cosine of theta was equal to u dot v divided by norm of u, norm of v. And that if u dot v equals 0, which is what corresponds to theta being pi over 2, or some integer multiple of pi shifted from pi over 2, if u dot v is 0, u and v are said to be orthogonal. Okay, so how can we shift that to this context? Well, it's not hard. We just we have the same symbol for norm, and instead of dot product, we put inner product. Okay. Now define cosine of theta equals inner product of u and v divided by norm u, norm v. Okay, and recall that norm of u is equal to the square root of inner product of u with itself. And if the inner product of u and v is 0, u and v are orthogonal. Okay, let's see this in action. We can look at a weighted inner product in R2. So let's use the example that we had before. So W1 equals 1 and W2 equals 2. Okay. So let's consider which vectors are orthogonal in this setup. So let's say we have u equal to 1, 0. Okay. What vectors are orthogonal to this? So which vectors are orthogonal to u? Well, the way we could solve that is by saying if u and v have dot product 0, that's the same as saying that 1 times u1 v1 plus 2 times u2 v2 equals 0. And because we know u1 and u2, we can fill those in, and this tells us that v1 must be equal to 0. Okay? So specifically, if I were to draw this on a graph, okay, if I have this vector, then these vectors would be, let's actually, so this vector in pink, then this dotted line in pink would be the vectors orthogonal to it. Okay, the ones where the x-coordinate is 0. So that's actually exactly the same as it would be with a dot product. But if we take a different vector, so let's say it's the vector 2, 1, okay, so here to be to have inner product equal to 0 means that 1 times 2 times v1 plus 2 times 1 times v2 equals 0. So that for us, this means that 2v1 plus 2v2 equals 0, or v1 plus v2 equals 0. Okay, so in particular, if we use this color, so 2, 1, so if we have 1, 2, so this is 2, 1. Oh no, it's too high. There we go, that's better. 2, 1. The vector orthogonal to that are the ones on the line y equals minus x. Okay, so it looks like, so as you can see, this is not, oops, let's get the rough outline. Okay, so these do not look like the just getting some dots. These do not look like they would be orthogonal under the normal dot product, and indeed they wouldn't be, but under this unusual weighted inner product, they are orthogonal. Okay. How about an integral inner product? What would that even mean for two things, to measure the angle between two functions? So let's see what that would be like. So let's look at the interval AB to be equal to 0, 1. Or let's make it simpler. We'll make it 0 to pi over 2. And we want to measure the quote-unquote angle between cosine of x and sine of x in this inner product space. So how would we do that? Well, we would start by taking u dot product v, and that's going to be, all right, where this we're representing by u is cosine x and v is sine x. So u dot v is the integral from 0 to pi over 2 of cosine x sine x dx. Okay. For those of you who remember Calc 2, we can compute this by taking 1/2 sine 2x dx from 0 to pi over 2. That's just a trig identity. And then we do a u substitution. We take 1/2. Now u is 2x. Okay, so this goes from 0 to pi. This is sine u, and we pick up, so instead of du, we get du over 2. Instead of dx, we get du over 2. Okay, so that's equal to 1/4 times the integral from 0 to pi of sine u du, which is 1/4 of minus cosine u from 0 to pi. Okay, so cosine of pi is -1, so it starts at 1, and cosine of 0 is 1, so it's 0. Okay. Okay, meanwhile, I don't have to, because u dot v is 0, I don't even have to write out u dot u or v dot v. So both of these will be non-zero because we know that these are only 0 when u or v itself is 0. So u dot u and v dot v, these do not matter. What we've learned is that cosine x and sine x are orthogonal as elements of the inner product space (0 pi over 2). And this is actually a really important fact which comes up in the topic of Fourier analysis, which some of you might encounter in the future. But for now, just kind of consider how weird this statement is, but how the various definitions we've made up to this point have made this completely reasonable. Okay, it's been a pleasure. Have a great day.